Welcome to the series of lecture on finite element analysis. In this part, we are going to see how to convert a beam problem into a mathematical model. In engineering, when we do the structural analysis, most of the machine members or structural members can be classified into three major categories. One is bar, another one is beam, third one is shaft. In case of bar, the load will be acting along the axis of the member. That is why it is called a axially loaded member. So the deflection also along the axial direction. But in case of beam, beam is a structural member which is subjected to transverse load. If you consider this is the axis of the beam, then the load is acting perpendicular to the axis of the beam. So that is why it is called a transversely loaded member. It may be a point load like this, or it may be a uniformly distributed load. The load will be acting perpendicular to the axis of the beam like this. And the third member is shaft. That is the member which is subjected to a torsion or twisting moment. In engineering, by considering these three members, bar, beam and shaft, we can easily solve any kind of problem. Now in this part, we are going to discuss about the beam, the types of beam and how to formulate this beam into a mathematical model. Since the load is acting perpendicular to the axis of the structure, the major mode of deflection in case of beam is like bending. If you apply a load perpendicular to this axis like this, it will tend to bend because this is like a curvilinear nature of deformation. So we need 2 degrees of freedom to define this type of deflection or bending. There are many types of beam based on the support or end condition. So if one end is fixed and another end is free, then we call it as cantilever beam. If one end is hinged support, another end is roller support, then it is called a simply supported beam. And we have a overhanging beam also. In overhanging beam, some length of the beam will be projected beyond the support, then it is called the overhanging beam. And the continuous beam, if the length of the beam is very large, then they will add some additional support in between the end support. So this is called the continuous beam. Fixed beam, both ends are fixed end. The another one is propped cantilever. One end is fixed and to support the length of the beam, they will provide additional support. This is called the propped cantilever and simply supported beam. Now, how to formulate a mathematical model for all these types of beam, that we are going to discuss. The mathematical formulation is going to be very easy. If you know the end condition properly, we can easily formulate the mathematical model that we will see. To derive the mathematical model, we are going to consider a simply supported beam with uniformly distributed load. So here the left end A we have a hinged support, right end B we have a roller support. The length of the beam is L. Throughout the length UDL is acting. The load intensity of the UDL is denoted by small w divided by unit length. Length of the beam is taken coinciding along the x-axis. Here x-axis is the independent coordinate axis. That is, along the x-axis we are going to measure what is the deflection of the beam. At left end A we can say x is equal to 0 and right end A we are going to say x is equal to L. These are the boundary condition for this beam problem. When you want to measure the deflection of the beam, so deflection of the beam is a transverse deflection here because deflection is happening perpendicular to the axis of the beam like this. Deflection is happening perpendicular to the axis. When you measure the deflection, we are using the notation y of x. Y is the transverse deflection. It is a function of x. So depends upon the position of the point we are selecting, the deflection will vary. So that is why it is called y of x. So y transverse deflection is function of the x. When you measure the deflection of the beam with respect to midspan, if you take any point in the left towards left side and right side, so we can get same amount of deflection on either side. To differentiate this deflection, Either this point is in the left of the midspan or right of the midspan. Let us say this is the point P and this is point Q. Let us say both have same amount of deflection. So to differentiate this position correctly, we are going to use the another variable which is called a slope of the beam. So slope theta is measured here. So theta one side is considered as positive and the another side is going to be considered as negative. So based on this theta, we are going to consider the position of the point. For all the beam problem, we are going to have 2 degrees of freedom as the variable. One is y of x, then another one is slope of this beam. How do you measure the slope of the beam? It is a first order differentiation of the variable y. So dy by dx is the slope. So by using this y and dy by dx, we can easily identify the point at which we are measuring the deflection. So for any beam problem, we have to use the 2 degree of freedom for defining the problem. Y of x and dy by dx are the variables. So it will have 2 degree of freedom. To make a mathematical model, the usual practice is we have to consider a small elemental length like this. So this is going to be considered as dx, the small elemental length. Now for this length we are going to introduce the shear force, bending moment and this load intensity, everything. Then we will derive the governing differential equation for this beam. When you consider a small elemental length, if you introduce all the forces to this small elemental length, then it is called a free body diagram. A free body is nothing but an isolated body from its surrounding, and you have to introduce all the forces acting on the body, then only it is called a free body diagram. So this is the free body diagram for this simply supported beam. The small elemental length is considered. For this length, the UDL is acting like this. The total UDL is W into dx. The length is dx. It will be acting at a middle dx by 2. So the W dx we can consider is acting at a dx by 2. We have to consider the shear force and the bending moment with the usual notations. We are going to assume the left side upwards, right side downwards, and here we are applying the positive bending moment. When you consider the shear force and bending moment, in the left hand side, when you say the shear force value is q, and the right hand side the shear force value will be having some small incremental in shear force, so that incremental value is considered as dq. In the left hand side we are considering q plus dq. Similarly, this bending moment is m. After passing through this dx, the bending moment value will be slightly increased. That incremental in bending moment is considered as dm. Here q is shear force, m is bending moment, w is load intensity, and dx is the elemental length. After drawing this free body diagram, we have to apply the equilibrium condition. Here we have both the force as well as the moment, so we are going to apply the two equilibrium conditions. First equilibrium condition, we are going to apply the force equilibrium. Sigma F equal to 0, that is equilibrium condition. The forces are acting vertically. Vertically upward is taken positive, downward force is taken negative. With this sign convention, when you add the forces acting on this free body, this is Q positive, Q plus dq is negative, this consider, and this W dx is acting vertically downwards at this point. This is also negative, so that is q minus W dx minus q plus dq equal to 0. Eliminating this q and q, we will get minus W dx minus dq equal to 0, which will going to give the important relationship dq by dx is equal to W. What is Q? Q is shear force. W is load intensity. So what is the physical meaning of this? The rate of change of shear force with respect to the length x, right? Rate of change of shear force dq by dx is equal to load intensity. This is one relationship we are getting through force equilibrium condition. Here we are going to use the moment equilibrium condition. In this case, we are going to consider the moment about the right hand side point. So at this point, the sign convention followed here is the counterclockwise moment is considered as positive, clockwise moment is considered as negative. With respect to this point, when you consider the moment, this moment is acting the clockwise direction, so minus m, and the q force is acting upwards, so it will form a clockwise moment. The distance is dx, so q minus q dx, and the w dx is acting in this point, so w dx acting downwards, so with respect to this point it will form a counterclockwise moment, so w dx into dx by 2, this is going to be positive. Then we have m plus dm, a counterclockwise moment that is taken here. When we simplify this one, the minus m and this plus m will get cancelled, and this dx is very small elemental length, so multiplication of 2 dx, we can eliminate this term. We will get q dx plus dm equal to 0, then which is going to give the relationship q is equal to dm by dx. So where m is bending moment, q is shear force, rate of change of bending moment is equal to shear force. Rate of change of bending moment with respect to length is equal to shear force. This is the second equation or relationship we are getting using the moment equilibrium. To get the mathematical model, we have to use one equation called the constitutive equation. Here we are going to use the bending equation as the constitutive equation because this is a beam problem. So bending equation, we know m by I, bending moment, I is the moment of inertia, is sigma b by y. Sigma b is bending stress divided by y. Then E by R, E is the Young's modulus, 1 by R the radius of curvature. In case of bar problem, I think you remember we consider free body diagram and we have applied the equilibrium condition. There we used the constitutive equation as the Hooke's law. Since the beam is subjected to bending load, we are using the bending equation as the constitutive equation. We will consider this m by I and this E by R. From that we can write m is equal to EI by R. In strength of material, we already studied that the relation 1 by r is equal to d square y by dx square, where y is the transverse deflection of the beam. This r is radius of curvature. Substituting this value, we will get ei d square y by dx square. This is nothing but bending moment. Bending moment m is defined in terms of the field variable y. The equation which relates the unknown under the field variable is called a constitutive equation. So here bending equation is the constitutive equation. So now we can understand bending moment is nothing but the second order derivative of the field variable. First we define the y of x is the transverse deflection, and the first order derivative of the transverse deflection is slope. dy by dx is slope. Now what is the second order derivative of this deflection? It is second order derivative d square y by dx square multiplied with ei is giving bending moment. After knowing this relationship, for bending moment m is equal to ei by d square by dx square, we will substitute this bending moment m expression in the equation 2, which is nothing but the rate of change of bending moment is equal to shear force, that equation. When you substitute this one, we are able to get the expression for the shear force q. After substituting, what you are getting, the shear force q is equal to ei d cube y by dx cube. Here you see the third order derivative of the field variable is shear force, that we have to understand. Now substitute this shear force value in this first equation. We will get ei d power 4 y by dx power 4 minus w equal to 0. This is the fourth order derivative of the field variable y. The fourth order derivative field variable is nothing but load intensity. Here we neglect this negative sign. This is going to be called as governing differential equation for the beam problem. What is this ei d power 4 y by dx power 4? It is also load. W is also load. It is a equilibrium equation. So this is a fourth order differential equation. This is called the governing differential equation for a beam. This governing differential equation is common for all types of beam. Then how to differentiate the types of beam mathematically. That is only based on the boundary condition we are going to apply. So that you will see. In case of mathematical model, we have to define three things. One is governing differential equation, another one is domain and boundary condition. Governing differential equation for this simply supported beam we derived ei d power 4y by dx power 4 minus w equal to 0. What is the domain for this one? The domain is the length of the beam, so which is varying from 0 to L. What are the boundary condition for this simply supported beam? At x equal to 0, that means left end hinged support, so transverse deflection y equal to 0, and this end allows the bending of the beam. The bending moment at this support is 0. Ei by d square y by dx square, what is this one? Second order derivative of field variable is nothing but bending moment, which is equal to 0 at x equal to 0. Coming to this right end, this is roller support, again deflection 0, so y at x equal to L, y equal to 0, and the bending moment is also 0 in this roller support. So ei d square y by dx square at x equal to L equal to 0. For mathematical model of a beam, we have to write the governing differential equation, domain, and this boundary condition. Only the boundary condition will give you an idea what is the type of beam. In this boundary condition, already we discussed, if the boundary is defined in terms of field variable, it is called a primary boundary condition or essential boundary condition. If the boundary is defined in terms of derivative of the field variable, then it is called a secondary boundary condition or natural boundary condition. That you have to understand. Coming to other types of beam, suppose if you have a cantilever beam, then how to write the mathematical model of a cantilever beam? Governing differential equation is same, ei d power 4y by dx power 4 minus w equal to 0. Domain is also same if the length of the beam is L, so x is varying from 0 to L. Boundary condition we have to write it carefully. So left end is fixed end. At the fixed end, deflection 0 and the slope is also 0. So y of 0 is equal to 0 and dy by dx, the slope at x equal to 0 is also 0, because this is for the fixed end. In the free end, it is free to deflect and also free to rotate. At the free end, bending moment 0 and also shear force 0. That you have to remember. Ei d square y by dx square is equal to 0. Ei d cube y by dx cube at x equal to L equal to 0. This is the boundary condition for free end. Boundary condition for fixed end, deflection 0, slope 0. Similarly, boundary condition for hinged end, deflection 0, bending moment 0, roller end also like that. So now coming to the fixed beam. Fixed beam, the governing differential equation is same. Ei d power 4y by dx power 4 minus w equal to 0. Domain is also, say the length of the beam is L, then x is varying from 0 to L. And what are the boundary condition? Both ends are fixed. Left end is also fixed, right end also fixed. How do you express the boundary condition? For fixed end, deflection 0, slope 0 at x equal to 0. Similarly, at x equal to L, deflection 0, slope 0. For fixed end, these are the boundary conditions. For free end, the boundary conditions are like this. Shear force 0, bending moment 0. For hinged support or roller support, deflection 0, bending moment 0. So in this way, you can easily remember the mathematical model of any type of beam. After knowing this mathematical model, we have to form the element characteristic equation for this beam to solve the beam using finite element method. So how to formulate the element characteristic equation of this beam, we will see in the next part. Thank you for your passion listening.